Okay, so to find this derivative, I want to observe a couple of things. One, we know when we have a sum or difference, we can just take the derivative of each part of the sum or difference, each term, separately. So we're going to do that. Then to take the derivative of the first term, notice that we have something with an x times something else with an x. And whenever that happens, you have to use the product rule. And then over here on the right, notice that we don't need a product rule because there's only one function of x here. But the power is not e to the x, it's e to the x cubed. So that is a composition of functions. So that means that we're going to need the chain rule. All right, so let's go ahead and start with that. Now, in the process of doing the product rule, we're actually going to have to do the chain rule as well. So we'll have to do the chain rule twice in this problem. Let's see how that works out. So first, let's remember the product rule. If you have y equal to some first function capital F times a second function capital S, then y prime is going to be the first function times the derivative of the second plus the second function times the derivative of the first. All right. We also need to remember that the derivative with respect to x of e to the x is going to be just e to the x. But the derivative with respect to x of e to anything other than x is going to be e to that power times the derivative of whatever it was to compensate for the fact that it wasn't an x. So, in other words, this is the chain rule version of the derivative of e to the x. All right, so in our product rule, the first function is the 4x, so this is our f, and the second function is our e to the negative 2x. So if our first function is 4x, its derivative, f prime, is just 4. And if our second function is e to the negative 2x, then its derivative will require a chain rule because we have something other than x in the exponent of the e. So we're going to take the derivative of that. Derivative of e to a power is just e to that power, times the derivative with respect to x of whatever that was. So that would be the derivative of negative 2x, which is just negative 2. So this derivative of this second function is negative 2 e to the negative 2x. Okay, so we have all the components we need for our product rule to take the derivative of the 4x e to the negative 2x part. So I'm going to go ahead and recopy my function down here. We have y equals 4x e to the negative 2x minus 3e to the x cubed. Then y prime is going to be, focusing on this part first, the first function f, which is 4x, times the derivative of the second function, which is negative 2e to the negative 2x, minus the second function, which is e to the negative 2x, times the derivative of the first, which is just 4. Now let's move on to the second term. Taking its derivative, we're going to have to use the chain rule. The negative 3 stays the same. The derivative of e to a power is e to that power. And then, since that power wasn't just an x, we multiply times the derivative of x cubed. So we have y prime equals, let's clean this up a bit, that's negative 8x e to the negative 2x minus 4e to the negative 2x. And then we're going to have the derivative of x cubed here is 3x squared. So if you multiply that times negative 3, you get negative 9x squared e to the x cubed. Now there's no one perfect way to write this expression, this derivative, so I'm just going to leave it in this format for now. It's possible that you would be required to write your exponents as positives moving into the denominator, but again, I don't see anything, for example, in common to all three to factor out that would make the expression look nicer. But you could play around with that, but there's not one perfect way to write the answer. Okay, so we're going to do one more like that and then we'll be finished. One more, meaning one more that involves a chain rule together with another type of rule. We don't have the one I was looking for. Let me go back over here. All right, let's use this one. Part B. We have f of x equals x over the cubed root of x squared plus 4. Okay, so the first thing you want to do when you see a root and you have to take a derivative, we don't have a rule for roots, so we're going to change it to an exponent format. So I'm not taking a derivative right now, I'm just writing it algebraically with a different symbol. So I'm going to use this as, instead of using the cube root, we're going to use power of 1/3. All right, the next thing I'm going to do is observe which operations are going on. I have something with an x divided by something with an x. That's quotient rule. And remember, for the quotient rule, you're going to think of the function f as the top divided by the bottom. And so f prime will be equal to the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. All right, in this case, what's our top function? Our top function, t, is just x. And what's our bottom function? Our bottom function is x squared plus 4 to the 1/3 power. We're going to need our top function, our bottom function, and the derivatives of each. So we need t prime. Well, the derivative of x is just 1, so that's easy enough. But the derivative of b, we have a power, something other than an x as the base. So we're differentiating with respect to x, so that means we're going to have to use a chain rule. So we're going to take the derivative as though it were just an x instead of an x squared plus 4 by bringing the 1/3 out front and subtracting 1 from it. But we're going to leave that x squared plus 4 plugged in, and then to compensate for the fact that it wasn't an x, we're going to take the derivative of x squared plus 4 and multiply it. So b prime, the derivative of the bottom, is 1/3 x squared plus 4 times the derivative of x squared is 2x, derivative of 4 is 0, so we don't need that. Oh, and I still need my power here. We don't want to lose that. Okay, so using the pattern bottom d top minus top d bottom over bottom squared, we have that the derivative of our function f is going to be the bottom, which is x squared plus 4 to the 1/3, times the derivative of the top, which is just 1, minus the top, which is just x, times the derivative of the bottom, which is 1/3 times x squared plus 4 to the negative 2/3 times 2x. all of this is going to be over at the bottom squared. So x squared plus 4 to the 1/3 squared. All right, so this looks very messy, but there's something you can do, and it works probably 80% of the time on these problems. What you want to do is to think of the numerator as two big terms. Here's one term, here's another term. And you want to factor out any common factors from the two terms. And this is going to help you to simplify the expression. You also want to factor out any fractions, even if they're not in common. So let's try that. So we have f prime of x equals, okay, we have a common base, which is x squared plus 4 and x squared plus 4. But what power do you factor out? So I just want to go off to the side here and remind you of something. If we had, say, x squared minus 5x cubed, what power of x could we factor out that's in common? You would factor out the lowest power, right? So you would take out the x squared, and that would leave you with 1 minus 5x to the first. Notice 3 minus 2 leaves a power of 1. You factored out the lowest power. We want to factor out the lowest power of x squared plus 4 as well. So what we're going to be factoring out is x squared plus 4 to the negative 2/3. Negative 2/3 is less than 1/3, so factor out the lowest power. Now I also said factor out any fractions that you might have. So you see how we have a 1/3 here? I'm going to factor that out as well. Remember, that has the effect of dividing by a third. So let's see what's left behind when I factor out the lowest power and the 1/3. So in the first term, since I've divided it by 1/3, that's like multiplying it by 3. So we're going to have a 3. And then we're going to need 1/3 minus negative 2/3. When you factor out negative 2/3, just like when I factored out x squared over on the left in green here, the x squared, I subtracted 3 minus the power of 2 to see how many powers of x were left. So for this power here, we're going to have to subtract 1/3 minus what we took away, which was negative 2/3. So that's going to add up to 3/3 or 1. That often happens, that the exponent goes away when we do this. So x squared plus 4 to the first power is left, and we don't really need to write the 1. All right, and then in the second term, we've removed the x squared plus 4 to the negative 2/3. We brought that up front. We removed the 1/3, and what else is left? Just negative x times 2x. All right, now that's all over x squared plus 4 to the 1/3 squared. When you raise the power to a power, you multiply the exponent. So that's just going to be x squared plus 4 to the 2/3 power. All right, now let's see why this is helpful, what we just did. So inside these parentheses here, the brackets I should say, we now have 3x squared plus 12 minus 2x squared. The 3x squared and the 2x squared combine, leaving just an x squared plus 12 in the brackets. Okay, and I'm going to bring my x squared plus 4 to the negative 2/3 down below, and I'm also going to think of this as this 1/3, bringing it out front. So the 1 is in the numerator and the 3 is in the denominator. So this is going to be 3 times, then we're going to have x squared plus 4 to the positive 2/3 times the x squared plus 4 to the positive 2/3 that was already there. Okay, so it's starting to look much better now. And we can multiply these two together by adding the exponents. So we have f prime of x equals, and we have x squared plus 12 over 3 times x squared plus 4 to the 4/3 power. So this is our derivative. So oftentimes when you use a quotient rule, and in the process you have the chain rule for a power function, it's very helpful to, at this step, factor out. Don't try to distribute or do anything like that. You're going to factor out whatever's in common. You're going to factor out the lowest power of whatever base and any fractions. The algebra can be challenging. Most of the time I see students get to the step where they have found the derivative, but the simplifying can trip them up. Okay, well, I hope this chat was helpful to you. If you did, please remember to give it a thumbs up. When you like it, it helps other students to find the video.